We are the second Autonomous Meteor Detector and Tracker team, Group 8. My name is Kate, my group members are Ben, Alex, and Sagi. Our clients are Stephen Knudsen and Chris Hurd. Our project was to design and build a low-cost, open-sourced, robust system to detect and track meteors that could be easily deployed by both astronomy enthusiasts and research groups. Never want to miss a shooting star again? We have good news for you. It's possible and it won't cost you a fortune. To track or detect a meteor, you need a long exposure photo to capture its trail in the night sky at just the right time. Existing night sky tracking systems are costly and difficult to operate, especially for hobbyists. Our system integrates a used DSLR camera, a Raspberry Pi board, and an open-source neural network meteor detection algorithm, all tucked inside a box and remotely controlled through a simple web interface. The project was successful. Our team designed and built an accurate and affordable system for continuous nighttime meteor detection. By separating software and hardware components, we achieved a flexible and customizable system. Despite some challenges, we delivered a fully functional prototype that can be deployed overnight.
When building our detector, we are careful in selecting components that would help achieve sufficient accuracy in capturing meteors, while being accessible for everyday people to obtain and operate. The system itself is enclosed inside of a waterproof breaker box, protecting it from a majority of weather conditions. An acrylic dome is also cut into the outside of the housing to allow the camera unobstructed access to the sky. The inner components of the housing include a camera mount to fix the camera in place, a power bar to supply line power to our system, and a fan for cooling during operation. For our choice in camera, we decided with a Canon EOS 350D due to its inexpensive cost and being an industry standard that's well supported by software and is familiar to hobbyists. Our system is run on a Raspberry Pi 5, which gives us enough performance to control camera operations, run our meteor detection, and send photos to an online database. To upload the photos, the Pi is able to communicate to the internet via an adapter that extends outside the housing during operation.
To set up the detector, first we open the lid, next we turn on the camera power, and finally we flip the switch on the power bar. The fans will kick on, and once you've seen the green light on the Pi, the detector will automatically connect to the web interface.
This is AMDT's web interface. It makes interacting with the system simple and easy. This is currently the home page, but there are 3 other pages accessible from the menu at the top. If we navigate to Configure, we can schedule the start and stop time of the system. For example, this is how we'd set the system to start in 3 minutes. Let's say at 4:03 p.m. and we'll run it for 33 minutes. Then hit save and we'll get some feedback that it has been saved and configured successfully. There are also quick start and stop buttons for ease of use and testing. If the system is plugged in within this time range that we set above, it will start immediately.
Once the system has been configured on the web interface, the detector will begin capturing images during the selected times and dates. In this demo, the system is on and capturing images. The system will continually capture images until the stop time and date are reached.
Users can view all the images captured by the detection unit on this interface as well. Pictures take just a few seconds to show up on the interface after they are taken. On the All Images tab, a user can look through the images, click through the pages, and they can also download a single image at a time with this button. As you can see, we have some different images. This is from one of our first test runs, a group picture. You can download an image, or you can filter the dates and then download all those images as a zip file. A user can also view only the images with detected meteors, according to our machine learning model, at this tab. It is the same interface as the All Images tab, but we will only see meteors. As you can see, we only have one picture of a meteor here, just for demonstration.
The housing is made from a commercially available junction box. The housing can be locked to safeguard the system from unauthorized tampering. Inside the housing, there is a power bar, a quick-release camera mount, and 2 ventilation fans. The quick-release camera mount allows users to easily swap or install DSLR cameras. The fans serve a dual purpose. They provide cooling for the Raspberry Pi, but also help to reduce condensation buildup on the inside of the housing. The fan intake is equipped with a magnetic filter that is easy to replace, aiding in minimizing the ingress of dust and bugs into the system. A sealed acrylic dome on top of the housing provides a hole for the camera to see out of. Finally, the system is fully sealed, so it can withstand all Canadian weather conditions.
Now, let's transition to the very heart of our Meteor detection system, convolutional neural network. Our machine learning model consists of 3 convolutional blocks, each followed by max pooling and dropout layers to avoid overfitting. At the output layer, we employ a single neuron with a sigmoid activation function to produce the final result. Is this image contains a meteor or not? Compiling the model, we utilize RMS propagation as an optimizer and binary cross entropy as the loss function. What's remarkable about our detection system is that it doesn't depend on the size of the image due to a very careful and precise pre-processing algorithm. Whether we are working with wide-angle shots or maybe high-resolution images, our system does a very good job extracting all important features to facilitate the work for the neural network. All in all, our model has demonstrated remarkable accuracy of 98.5% rate. However, rather than talking about numbers, let's actually see how our neural network behaves on 2 testing images. So, in this image, we have a clear night sky with a few stars and a meteor trail. Now, in this image, we have a bit of dirt on the camera lens, a large source of light, and a lot of rays coming out of it, which have a high chance of being identified as meteor trails. Now, let's run our CNN. First things first, you might be wondering what happened to our images. The answer is simple. They were preprocessed to extract the most important features and compress the image to a square size of 256 by 256 pixels. As we can see, our model correctly identified the presence of the meteor in the first image and its absence in the second, despite how many rays and light we had there. Let's move on and talk about what worked and what didn't work. Our system is capable of taking pictures with 30 seconds exposure and is capable of sending them over the network so that end users can view them through a very intuitive, easy to use and quite appealing web interface. The machine learning algorithm is precise and deployed locally, which makes our system a standalone product, while our housing can withstand standard Canadian weather. So what didn't work? Detection software cannot run without internet connection, which introduces large delays if the connection is unstable. In addition, we initially wanted to use Raspberry Pi 4 because of its affordability, but it provided too little computing power to host a whole CNN on the board. Talking about the boards, we also considered using Jetson Nano to enhance the detection algorithm, but its integration introduced delays in development. Now, what can we do in the future? Firstly, we can definitely enable support of offline detection. The framework for building offline functionality has already been established. The machine learning model and camera control algorithms don't require any network connection to function correctly. Secondly, we can have another camera for video recording. A secondary camera with video taking capability would improve further tracking calculations and supply more data to the end users. Lastly, we can easily integrate online diagnostics. With online diagnostics implemented, the system can provide an accessible method for end users to debug and check the system status without having to manually retrieve and diagnose the physical device.
Overall, we are able to build a camera system that can be deployed and survive the outdoors, continuously capturing quality pictures of the night sky. The materials used in its construction were chosen to be consumer accessible and emphasize modularity. The system also included features to enhance and simplify its use, including a machine learning module that could sufficiently detect mirrors and photos, and a web interface to remotely control and view data on the system. In prioritizing simplicity and accessibility, we strive for our device to be a stepping stone in making these atmospheric events easier to experience for a wider range of people. In breaking down these barriers, we hope to get more people out there looking for meteors. Thank you very much.